Hi everyone. So this video is an introduction to a very interesting regularization technique that's particular to deep learning, which is dropout. And dropout basically addresses a very important problem with bagging or ensemble methods in general, is that it's usually computationally expensive to implement an ensemble method, because basically you have more than one model, right? So your training time would basically add up or linearly with the ensemble size, right? So instead of one model, let's say, taking 1 minute to train, you need 10 models taking 10 minutes to train, and so on, right? So what Dropout does is the following. It basically, for each example in a mini batch, so every time I load a training example, okay? And don't worry for now about the term mini batch, and that we'll address in the next section when discussing mini batch optimization training. Now, every time we load a training example, we randomly sample a different binary mask, and we apply that mask to all hidden and output and input units. Binary means that, so mask means a vector, right? Corresponding to the number, that vector has a length corresponding to the number of hidden and input units. And then binary means 1 and 0, right? If the value of the mask element corresponding to a unit is 1, we keep that unit. If it's 0, we drop that unit, right? So for every example, I have a different realization of my network, right? And typically we use a probability of 0.8 for the input units, right? For keeping the input units, and the probability of 0.5 for dropping or keeping the hidden units. But these probabilities really change with application, and it depends a lot on trial and error, right? So basically, the higher the probability, the sparser the network that you obtain every time you load a training example. And then you train and update the parameter corresponding to the realization of that example, right? So it's as if, why is it considered an ensemble method? Because we think of every realization of the network, meaning that if I have a network with, let's say, 2 input units, and then 2 hidden units, and then finally some output units, right? Then if I do dropout, I think of the network without that unit as this is a realization of the network, 1 input unit and 2 hidden units. And another network with that unit existing and the other input unit not existing. That's another realization. And one with the 2 input units existing and the first hidden units non-existent. That's a third realization. And one with the 2 input units existing and the second hidden unit non-existent. That's a fourth realization, right? So in general, if you have n hidden and input units, you have 2 to the n realizations of the network, okay? And then basically the aim of dropout is to minimize the expected value over the mu, which is the mask vector, over all realizations that's possible that you can get from the network, right? So this expectation contains exponentially many terms. Exponential in the number of hidden and input units, right? We said if you have n, you would have 2 to the n realizations. Here we have 4, we would have 16 realizations, right? So we only discussed the 4 realizations where 1 unit doesn't exist. But there will be realizations where maybe the 2 hidden units not existing, right? Not all 16 will be valid, because the 2 or the 2 input units do not exist is a useless realization, right? So that should not update the parameters in training, because basically the outputs will be 0 anyway, regardless of the weight parameters. But or will be equal to some statistical mean regardless of the value of the weight parameters. But the number of valid realizations will still be exponential. right? So as I increase the number of units from 4 here to 64, the number will increase proportional to the difference between 16 to 2 to the 64, right? So the expectation contains exponentially many terms, but the hope is to obtain an unbiased estimate of the gradient by sampling values of mu. And then actually computing that expectation as a cost function is a very expensive thing to do, right? Because you want to take the expected value over all possible realizations. And Dropout relies on a very interesting concept which is called the weight scaling inference rule, and we'll discuss it in the video after the next. We will discuss it in the video after the next. So in the next video, we'll discuss the difference between dropout and bagging, which is basically a very interesting analogy. And because you can think of dropout as bagging between the different realizations of the network, right? But these realizations are not really independent models because they share parameters, right? So for example, here, these two realizations right here, this one and this one, they share the parameters of the first input unit. So of the first input unit connected to the first hidden unit, right? This realization and this realization share the parameter of the first input unit connected to the second output unit, right? So this parameter here is shared here. This parameter here is shared between these two, right? So we have parameter sharing between the different realizations, right? And that's one major difference between bagging. Another major difference between dropout and bagging is that in dropout, actually, typically most realizations are not explicitly trained at all, right? So for every training example, I draw a random realization of the network depending on the dropout probabilities, right? Some of the realizations may never appear during training, and yet I am optimizing with respect to the expectation over all possible realizations. And really what's enabling us to do that and to hope that the estimate that we have is approximately unbiased and hence really reflects this expectation is what's called the weight scaling inference rule. That rule is very simple, which is basically during inference, we scale every weight by the dropout probability. We will discuss it in more detail and the justification behind using it and how it's enabling us to obtain an unbiased estimate of the gradient in the video after the coming one. Sounds good? Yeah, thank you.